there yet. So I'll start this. So the streaming is now begun. I need to wait for a second. So, there you go. And then I will share the screen. You see that, yeah? And then in a minute, I'll begin. Yeah. So far we're about 100 between live streaming and here, but it takes a minute or two to people to show up. Let me see if Martin, nope. Burkhard, not, and Karen. So it's the problem when people are local, you know. People that are local don't seem to not need to go on online. That's funny. Okay, so I think it is time. So let me begin. Today, once again, thank everybody, 100 or so of you to come to the online SPICE-SPIN+X seminar series organized, I guess, by me, comes to say at the moment, at the end, but in reality, with the support of my own center, and of course, on the SPIN+X Collaborative Research Center, led here in Mainz by Matthias Chloe, and in Kaiserslautern by Martina Schliemann and Burkhard Hillebrandt. As you know, this is an online webinar format, and then you will see the speaker and this presentation, and then please write your questions in the Q&A, and I will afterwards give you the microphone to be able to ask the questions to Helen. So Olena Gomonay, which is known as Helen to all of us, is now a very, very well-known person within our antiferromagnetic spintronics field that is emerging, but had been doing this for quite a long time. Actually, she was actually got to know her from a fantastic review that she wrote at some point, and I had to find her and try to attract her to Mainz. And I think during my whole career in Mainz, I've gotten many comments that my best finding in Mainz was to find her and attract her to here. So this an expert on antiferromagnetic spintronics, magnetoelastic effects, and phase transition theory, and it's now here, and it's been with us for quite a few years, and we're looking forward to many more years. So I'll stop now sharing, and I will ask Helen to please go ahead and share your screen, share your presentation. Okay.
One moment.
Yeah. Oh, Burkhard, sorry. Let me put Burkhard just arrived. I'll put Burkhard as a panelist.
Okay.
Thanks for coming, Burkhard. Okay.
And yeah, what's the time?
Yeah, well, yeah, it's okay. That's the whole point of online. You can be just on time. So go ahead, Helen, go ahead and start, and I'll turn off my microphone, and if there's an interruption, I will let you know. Okay.
Thanks a lot for this kind introduction, and it's a great pleasure for me to participate in a SPICE seminar. So I'm a member of the SPICE group, and today is a peculiar day for people from Mainz, because today is an Ash Wednesday, when the Fastnacht, famous Mainz Fastnacht, is at its end, and we should stop of having fun and start working hard. But I will try today to give you a little fun still by talking about magnetoelastic effects in antiferromagnets. So why should we pay attention to magnetoelasticity? So if you try to Google visualization of ferromagnetic domains, then immediately you get 100 or 1000 pictures taken by a very poor and primitive microscope or a little bit better microscope, but still it's quite easy to get an information about a ferromagnetic structure. But if you try to do the same thing for antiferromagnetic domains, then you end up with a pictures taken at synchrotron by XMLD technique, which is extremely involved, or by other involved techniques like spin polarized STM, which needs monolayers and very specially prepared surfaces and sample, etc. So antiferromagnets, they are very interesting for spintronics because they are robust to the external fields, but this makes them very difficult for direct observation. However, the antiferromagnets show a quite pronounced magnetoelastic coupling between spin and lattice. And we can use this. And instead of looking at antiferromagnets by light or X-rays, we can try to listen to them. We can try to apply strain or stress to look at the strain response and then reconstruct the magnetic structure of the antiferromagnetic textures. On top of these magnetoelastic effects could be very useful for application, as we know, for example, from the straintronics, which at the moment are well developed in application to ferromagnetic materials. So to make first steps and to understand which magnetoelastic effects could we achieve in application to antiferromagnetic materials, we decide to look at the antiferromagnets and to study magnetoelastic effects as a first step in statics and in some more or less understandable conditions. So today I will try to explain you and to convince you that the strains are extremely important for antiferromagnets, and they can control the dynamics, they can control the morphology and antiferromagnetic textures, and then they can be used as additional tools for manipulation of our spintronic devices. In my talk, I will discuss some basic concepts of elasticity, which maybe are not so well known to the magnetic community, such as frozen strains, spontaneous strains, and compatibility of strains, and so on. And we'll try to illustrate these concepts, giving some physical examples which result from our recent developments in Mainz, and also in with other groups. And at the end, I will try to give an outline of possible directions in which this magnetoelastic theory can be developed further. So I start from the concept of frozen strains and spontaneous strains. So let's consider an antiferromagnet which in a paramagnetic state has a tetragonal lattice. When it goes through the nail point, the lattice try to deform, and corresponding deformation is associated with the orientation of the nail vector. And if this antiferromagnetic sample is homogeneous and infinite, we call corresponding deformation spontaneous strain. And this spontaneous strain corresponds to the condition of the stress-free sample. Though spontaneous strains maps distribution of the nail vector, and they look like some secondary order parameter, if you wish, they can play a very important role in dynamics. But before discussing the dynamical effect, let's compare the characteristic time scales of the elastic system and magnetic system. So characteristic magnetic times, as we hope in antiferromagnets, are of the range of picoseconds, so 10 to the minus 12. The characteristic times of the lattice depend on the size of the sample, but even for very small samples of micron size or 100 of nanometers, they are much larger, of the order of 10 to the 9 and more. So the lattice is much slower compared to the magnetic subsystem. And in many cases, we can consider the strains which are formed when crossing the nail point as frozen into the sample, and consider dynamics, magnetic dynamics induced by external fields on top of these frozen strains. So this concept is called frozen lattice or frozen strains, and these spontaneous strains they modify anisotropy of an antiferromagnet. So to illustrate this modification, let's again consider a very simple example of an easy plane antiferromagnet with tetragonal symmetry. So here at the left right panel, you see the profile of the energy, which has fourfold symmetry and two easy direction for the nail vector. However, if we start to increase spontaneous strains, then these strains removed generously between two otherwise equivalent states. And the energy profile loses its tetragonal symmetry. So now we end up with only one state which has minimal energy, and the other state is metastable. So this was a well-known effect in 60s, as usually Russians did everything at the time. And but this effect was considered in application to large homogeneous samples, and it showed up in the magnetoelastic gap in the spectra of antiferromagnetic resonance. However, today we are talking about other effects related with spontaneous strains, which we can find in multi-domain samples. So let's consider a very simple example of an easy plane antiferromagnet, which has two domains, as shown in this figure. So if we forget about elasticity at all, then the magnetic texture in this sample varies from left to right, and the energy profile in the left and right hand side of the sample is the same. It has tetragonal symmetry. So in this case, the anisotropy of the system is spatially homogeneous, and then if we calculate the dynamics of the domain wall, we found out that the domain wall in this case can move freely without activation barrier. And this result is well known from the theory of solitons. No activation energy, no frequency, no pinning. However, if we now consider the same easy plane antiferromagnet, but we take into account spontaneous strains, then situation will be quite different. So here you see the same magnetic texture shown by arrows, and this texture evolves on top of the spontaneous strains shown in black and orange with colors. These spontaneous strains, as it was already mentioned, modify the profile of magnetic anisotropy, as is shown by this butterfly instance. So in left and right hand sides of parts of the sample, we have different orientation of the easy magnetic axis. So now imagine that the domain wall shifts with respect to the spontaneous strain field. What happens? In the area which is delineated by the rectangle, we find out that the nail vector points out into not easy magnetic direction, but in the perpendicular direction, which corresponds to a metastable states. So the displacement of the domain wall in this case is associated with the increase of the magnetic energy. And if we look then at the dynamics of the domain wall, we will find that the domain wall is pinned. So if we try to move it, it will oscillate in the vicinity of this magnetoelastic domain wall. And it has non-zero frequency, whose value scales with the value of magnetoelastic interactions. Such pinning of the domain wall is a result of the inhomogeneity which is induced by the spontaneous strains into the sample. Interestingly, the frequency of the domain wall in this case, of course, it grows with the value of magnetoelastic constant is shown in the left panel, but it is always below the continuum, below the frequency of the antiferromagnetic resonance. So the domain wall in this case can be considered as a localized excitation which should be added into the magnon spectra. And this localized domain wall can modify also dynamics of magnons. For example, it can induce a strong reflection of the magnons from the domain wall, as shown in the left panel. So the higher the magnetoelastic constant is, the larger is the reflection coefficient. More interesting effects and more peculiar effects appear in the antiferromagnets, which have some special kind of domains, so-called T-domains. And a good example of such an antiferromagnet is given by nickel oxide and also cobalt oxide crystals. So in these materials, the magnetic ordering, the Néel vector is parallel to 111 crystallographic plane. And as we have 4 types of 111 planes, we have 4 types of T-domains. Interestingly, these T-domains have different, not only magnetic order, but also they have different distortions. And these distortions are very large because they are induced by strong exchange restrictions. So if we consider a domain wall which separates 2 T-domains, so these domains are called twin domains or T-domains, we found out that in this case, not only orientation of the easy axis is different in left and right domain, we find out that also orientation of the easy plane is different. So what can happen then? Then we understand that in this case, we again have anisotropic, we have a space-dependent anisotropy field with space dependence of all possible directions defining easy and hard magnetic axis. The effect of such inhomogeneity we can feel when we look at the spectrum of magnon modes. So it's quite clear that the magnon eigenmodes of the homogeneous sample and a multi-domain sample should be different. And considerations are very simple. So in a homogeneous sample in T-domains, we have modes which are polarized out of plane, but in the other T2 domains, this out of plane direction is absolutely different. So this means that the mode which is polarized out of plane should split into 2 in and out of plane modes when going through the domain wall boundary. And this effect is very similar to the effect of the optical birefringes when the optical ray goes through the sample and then splits into 2 rays with different polarizations, different wave vectors, and the same energy. So we can say that magnetoelasticity is responsible for possible magnon birefringence effect in a case of T domains in nickel oxide. Of course, the domain wall in this case is also can be considered as a localized magnon mode, which has a little bit more complicated structure. And this localized mode can result in other very interesting effects. If we go beyond the linear approximation and consider nonlinear effect in the nickel oxide, then the domain wall can participate or mediate parametric down conversion of the high frequency modes with a small wave vector to the low frequency modes with also small, almost K0 wave vector. This effect was recently observed experimentally in ultra-fast pump probe experiments with nickel oxide, as shown in the left panel, left top panel in this slide. Now, I would like to switch to the other concept of elasticity, incompatibility of strains. And this concept is not so common, so I will explain it using two examples. Let's again consider an antiferromagnet grown on top of a non-magnetic substrate. And let's assume that in a paramagnetic phase, the lattice of two layers is the same. Then what happens when this sample goes through the null point? The upper antiferromagnetic layer will try to deform due to magnetoelastic interactions and spontaneous friction. But the substrate is non-magnetic and it will try to preserve its initial form. This can create a conflict at the interface between an antiferromagnetic and non-magnetic layer. So the strains, spontaneous strains in antiferromagnetic layer are incompatible with zero strains of the substrate. Another example can be given by an antiferromagnet with different magnetic domains. So these domains could be deformed in a different way. And at the arbitrary interface between these domains, we can again find that the strains do not fit each other and create incompatibility between deformed regions. So this incompatibility seems to be an intuitive concept, but in elasticity theory, it has a very accurate definition through mathematical symbols. And in fact, this incompatibility is a tensorial analog of the curl of the vector. And in elasticity theory, this concept of incompatibility is used when people try to describe what happens in materials with such structural defects as disclinations shown in figure or dislocations. The incompatibility created by these types of the defect is the source of additional strains in the sample, which try to relax this incompatibility. These strains are usually called plastic strains. So we believe that in an antiferromagnets, these kind of defects, elastic defects, could be attributed to the incompatibility between the spontaneous strains in which maps a distribution of the null vector in antiferromagnetic textures. To give an idea how this incompatibility can work in real cases, I will discuss now some recent effects which were discovered by Chloe group as experimentally. So these thermomagnetoelastic effects. So we start from a very basic or standard experiment in which we would like to switch an antiferromagnetic insulator using SPIN+X. And for this, we usually put a platinum electrode on top of the sample, as shown here. But these electrodes have some special structure. For example, they have a cross, they make a cross. And then the current which flows through this structure is strongly inhomogeneous. You can see these hot corners with high density of the current and blue regions where the current density is quite low. Due to the Joule heating, such inhomogeneous distribution of current creates an inhomogeneous distribution of temperature. And as a result, this temperature effect induces inhomogeneous distribution of volume expansion of underlying antiferromagnet. So you may ask, what has to do with the switching between different antiferromagnetic states? Here we are talking about some scalar effects. Temperature and volume effect are isotropic, and we would like to switch between different directions of the vector, of the Néel vector. But here, this incompatibility comes into play, and I will try to explain how this chain of heating and expansion can lead to the switching using the following cartoon. So here I show the temperature gradient, so the temperature distribution. Hot places are red and cold places are blue. And this temperature distribution induces some volume effects, which are shown with the squares. And it's natural that the volume effect, volume expansion, is proportional to the temperature. So locally, so the volumes in different areas are different. So if we look at the interface between cold and hot region, we see that these both squares do not fit each other, so they have different lengths. So we have incompatibility of strains, and this incompatibility should be compensated by some plastic deformations, which are depicted here with the ellipses. And what is nice, these plastic deformations are shear deformations in the sense that they have some preferable axis of elongation. This axis of elongation has a different direction on both sides of the interfaces, but if we sum up all the contributions inside the center of the cross, we found out that the average strain in this region has preferable direction, vertical in this slide, and this preferable direction of striction through magnetoelastic mechanism sets a preferable direction of the Néel vector. So we can conclude that such thermomagnetoelastic mechanism can choose this or that orientation of the Néel vector locally and induce switch. And if we look at the formula and compare magnetoelastic contribution with Zeeman energy, we see many similarities, but magnetoelasticity gives much more possibilities because we can vary sign, we can make it inhomogeneous, and so on. And this theoretical picture was it's not only a theory. It was proved in the experiments directly. And first, what we did, we tried to use a different geometry of electrodes as shown in this slide. So we used 2 electrodes, so we used the cross which consists of 2 electrodes and only 1 electrode. The current flow only through 1 electrode, the other was idle, and we tried the other geometry where the current flowed through pairs of electrodes, both pairs of electrodes, and then this induced a different distribution of strains as shown in the middle panels of this slide. And depending on the geometry of the current and heating, we could switch the anneal vector either parallel or perpendicular to the current direction. And this effect could be explained only by thermo-magnetoelastic mechanism, because spin-orbit torques are usually switch the anneal vector only in one direction with respect to the direction of current. To be more sure that the thermomagnetic elastic effect is responsible for switching in nickel oxide, we went further and we made a hole in the platinum electrode to avoid a direct spin orbit torques, creation of spin orbit torques in the center of the devices. So the current was able to hit the central area, but was not able to create the torques, and in this way, as we have seen the switching, we were sure that the effect is related with a thermomagnetoelastic mechanism. And of course, this switching is consistent with dynamics of antiferromagnetic system induced by the external strains, current-induced strains. And you can see these in the experimental slides in the left and right, and simulations in the center of the slide. So with this, I came to the third part of my talk, where I would like to give some ideas how the theory of magnetoelasticity could be developed further and which effect we can anticipate from it. And I will mostly discuss the problem of the equilibrium domain structure and domain textures in antiferromagnets. And here we have 2 problems. One is soft, one is hard. And the soft conceptual problem is that there is no visible reason for antiferromagnets to form equilibrium domain structure. If we turn to ferromagnets or ferroelectrics, we know that there the magnetic or ferroelectric order parameter creates magnetic fields, and moreover, the divergence of magnetization, so the inhomogeneity of the magnetization, is a source of additional fields, which are called magnetostatic fields or demagnetizing fields. These fields are long range, and thus they can create the domain structure which fills the whole sample, which is sensitive to distribution of magnetization as a whole sample. In antiferromagnets, the order parameter does not create any physical field. So we have a problem. However, if we turn our side to the elastostatics or elastical system, we see a lot of similarities between the equation of magnetostatics and elastostatics. First, incompatibility is very similar to the magnetic charges, the divergence of M. The equations of elastostatics have the same mathematical properties as solutions of the magnetostatic equations. So they are long range, and so then they could be responsible for formation of non-trivial textures. And then we can remind that in an antiferromagnets, the spontaneous strains are related with the distribution of the Néel vectors, and in such a way, the magnetoelastic mechanism can be responsible for creation of long-range fields and domain structure formation. So we tried to play with this idea and calculated, for example, so-called distressing energy. And this is energy which has its analog in ferromagnetic materials. In ferromagnetic materials, we calculate demagnetizing energy, which should be zero if the average magnetization of the sample is zero, and similar can be demonstrated for antiferromagnets grown on non-magnetic substrate. The distressing energy scales with the volume of the sample and should be minimized when all the domains with different deformations are equally represented. Also, we can find a similarity between the block and nail walls in ferromagnets and different types of the domain walls in antiferromagnets. In ferromagnets, block walls are believed to have lower energy because they are not associated with magnetic charges, and nail walls produce this divergence of M and charges. And the same can be applied to the antiferromagnetic domain walls. In this case, it's called Nye walls, the walls which do not have any incompatibility. And this concept was first introduced also many years ago by Kleman and Milt in application to ferromagnets, but we can also use it for antiferromagnetic materials. So if we look at an antiferromagnet, which has two types of the domains with different deformation, then for generic orientation of the domain wall, the length of the magenta and blue region is different, and this creates a problem in compatibility of strains. So then the energy of such domain wall should be higher. But if we try to find another orientation, we can find two of them, and for which the length of red and blue region is the same, and these orientations correspond to the minimal domain wall energy, and this can be also calculated directly. So the contribution of magnetoelastic energy of the antiferromagnetic domain wall depends on the orientation of the domain wall as a cosine squared, and then it's obvious that there are some directions which correspond to the minimal energy of the domain wall, and in this case these are hard magnetic directions. So we can summarize these and anticipate the domain structure in an infinite blanket film of an antiferromagnet grown on a non-magnetic substrate. So this domain structure should consist of the domains of black and white of different types, equally distributed, with a flat boundaries which have the certain orientation along hard magnetic direction. And we hope that this is similar to what we usually see in the experiment shown below. So it's XMLD, a very complicated experimental technique. So this idea of magnetoelasticity can help us to solve some conceptual problems related with the creation of equilibrium antiferromagnetic textures, which can be reversibly manipulated by the external field. But we still have a hard problem, so a technical problem. For ferromagnetic materials, we usually use micromagnetics in order to calculate distribution of the magnetization in space. And there are a lot of micromagnetic technique which is developed. It can also include long-range interactions, so demagnetizing energy. So as far as I'm aware, it's quite tough and time-consuming to implement this part of calculations. We suggest to try to find similar things in application to antiferromagnets. So in principle, we can imagine the micromagnetic software, which can predict the distribution of the Néel vector in antiferromagnets. But here we face a lot of difficulties. So we can reformulate the problem of antiferromagnetic structure in terms of the Néel vector by introducing this distressing energy, which involves implicitly the magnetoelastic interaction. We still find out that the expressions for the distressing energy are more complicated compared to the ferromagnetic case. They involve 4 components of antiferromagnetic vector instead of 2 for ferromagnet, and they involve tensorial green functions and so on. But this is hard, and this is nice because then it opens a lot of problems for young people, and then the progress that does not stop with my talk, I would hope. So I'm at the end of my talk now. Oh, sorry, I would like to make conclusions. So we considered dynamics of the domain wall, which was related with magnetoelastic interactions. And we found out that these strains could be extremely important and change significantly the magnon spectrum and the dynamics of the domain walls. We found out that the strains can affect the domain structure and can be responsible for formation of the domain structure, and also strain is very important for switching and for application in the real devices. And now I show my collaborators, not all of them, but yeah, so I'm very happy to work with different experimental teams and hope that you see I have a lot of space here for other people. So thank you. And
thank you. So, thank you very much. And I think you're probably the only speaker that finished online on time.
I was well trained by you.
Yeah, you're extremely proud of you. So let me begin the questions. So Vlad, could you please go ahead and unmute yourself and ask a question?
Can you hear me?
Yeah.
Hi, Helen. Thanks for a nice talk. I always learn a lot from it. I have a question about simulations. So as you showed in the beginning that I just can modify my symmetry of my unit cell in order to simulate such elastic contribution to antiferromagnet. Is it enough, or I also need to do something else?
Are we talking about some DFT calculations, or we are talking about
dynamics?
Dynamics. So the model which I described here is based on the idea that there are spontaneous strains in the materials, and these spontaneous strains is something inherent to the material. So I cannot took this spontaneous strain at my will. They are related with the material properties. But on top of this spontaneous strain, I can add additional external strains and also modify dynamics and distribution of the magnetic vectors. So you can do both. You can assume that you have strains, implement them, and then look at the dynamics on top of this, or you can try to look at the strains which are created by the external fields.
Okay, I'm just wondering about this model of frozen spins. So if I so to include this strain, I only can modify anisotropy term because of this.
Yeah, exactly. So sorry, I did not understood it properly. So yes, once you assume that you have this strain field somehow distributed in your sample, then you can recalculate it, implement it into the space-dependent anisotropy profile, and then forget about strains, as long as your magnetic system is much faster than the lattice.
What about symmetry? So on your simulations, it looks like you consider cubic symmetry, but you need to consider something lower symmetry system, right?
Once you introduce strain, the symmetry is lowered locally.
Okay, so I can remain in the same symmetry basis, it's orthogonal basis.
Yeah.
Okay.
So let's go to the next question. Is from Pablo. So Pablo, go ahead and mute yourself. And
thank you very much for a nice talk. I have questions regarding this thermo-magnetoelastic effect. So is there any anomalous contribution, something similar to anomalous Hall effect in your case?
Do you mean this asymmetry of the contribution of the strains into the magnetoresistance?
Yes.
I think it could be. Of course, this strain variation can also affect the SMR signal or AMR signal and so on. But there are two factors. First, if we look at the redistribution of the domains, then we see it in the SMR. And this redistribution of the domains, it can be related with strains. So in this sense, we can feel or can measure these strain effects by SMR. Then it could be direct contribution of the strain into the value of resistivity. But I can guess that it would be very small because these strains which we discuss here are of the order of 10 to the minus 5, 10 to the minus 4 at most. So I'm not sure that such small strain can modify significantly or can be visible in the experiment on SMR.
Okay, maybe a second question regarding the other antiferromagnets, for example, topological antiferromagnets such as mangan-3, stannum. Are magnetoelastic effects important there?
So, as I am working with my magnetoelasticity, I will look for magnetoelasticity in any material which you suggest to me, because I am biased. So my answer is yes. If you show me manganese-3 stannum, I will find some magnetoelastic effects there.
Okay.
let me ask.
But seriously, yes. With manganese-3 stannum, I think.
So for Volodymyr, go ahead and.
Hello, Helen, and thank you for nice talk. I have two questions. The first one is about this self-spin domain wall, which is self-spin because this spontaneously induced strain. So this effect, can one expect the same effect for skyrmions? And if yes, then I think it makes sense to recalculate the magnum spectra on such a kind of skyrmion. What do you think?
First of all, I was inspired by our joint work on skyrmions, working on this localization of the domain wall. So then my answer is yes. I think that it can also be interesting to look at the skyrmions in presence of these strains, and it can pin off for sure.
And change the spectra of magnets, I guess, as well as for domain wall.
Yes. The structure, the distribution of the magnetic modes, and so on.
Yeah, thanks. And the second question is about this analogy between strain and magnetostatics. In case of magnetostatics, at least on intuitive level, we have separation of volume and surface charges, magnetostatic charges. For example, in this example, which you presented about Bloch and Néel domain walls, so this is only in a bulk. Bloch domain wall is more energetically preferable if you have surfaces. Néel wall can be more energetically preferable. But my question is, this separation about for magnetostatics, for volume effects and surface effects, can it be also applied for strain? Can you say there are different, like strain, not charges, but something similar on surface and in bulk?
Exactly. So the analogy is full, I would say. So we can introduce these bulk charges, surface charges. This is a boundary conditions, and that's all. And the difference between magnetostatics and elastostatics is only in the mathematical form. So this elastic theory is more complicated because you are working with the tensors instead of vectors. But all the mathematical answers are very similar, and this similarity was pointed out many years ago by Eshelby. So it's known in elasticity theory.
Thank you.
Okay, so Christoph, go ahead and ask your question, please.
Yes, Helen, thank you for this interesting talk. I have a question concerning your part incompatibility of strain. So you were talking about a thin epitaxial film on a substrate, and I was wondering what will be the effect of the film thickness when you compare a very thin film to a very thick film, because then you will also have a different density of this location and so on. So what will be the effect on the of the film thickness?
Intuitively, I would say that it would be similar to what we observe in ferromagnets. This branching effect. So close to the surface, you have a tiny structure, and in case of antiferromagnets, you will have tiny domain structure in a very thin films where this interaction between the substrate and antiferromagnetic layer is strong. Once you have a thicker film, then far from the interface, these strains would be relaxed somehow, and then the domains will become larger and larger.
Okay. But if I consider now a thick film, you would say that close to the interface, it will be independent of the film thickness. So when I only would look very close to the interfaces, would the film thickness play an important role or not?
I would say yes and no. So of course, if you have a thin film, then it's also important what you have on top of this on the other interface of an antiferromagnetic layer, whether you have another layer of another material or it's a free surface and so on. So in principle, you can look at this as a condenser. So you have some boundary condition at one interface, but then you have a free interface in which something should also happen. And once these magnetoelastic interactions are long range, they fill both interfaces.
Okay.
So the thickness matters.
Okay. Okay. Thank you very much.
The next one, Michael. We'll try to get to everybody. I'm just trying to follow in order here. So go ahead, Michael. Your question.
Yes, thank you. Maybe I didn't listen to everything because I was disconnected for some time. question is, can one achieve the magnetoelastic effect or this domain configuration also by acoustic excitation? Or in other words, you shout at the material and the domain formation changes?
Yes, I think yes. And recently I came across a paper which considers the motion of the antiferromagnetic domain walls in the presence of the stress waves. So of course you can induce domain wall motion and different dynamics with the acoustic waves, but the question is what is the wavelength? So if you are working with the meters, if acoustic wavelength is very large, then it's like a homogeneous strain. So
well, I
need,
was thinking that you could drive the domain wall by the acoustic wave in a certain direction.
Yeah, of course. If
okay.
the material is magnetoelastic, then yes.
Okay. And the magnitude of the required strain, is it 1 per mil, or can one estimate that?
It's very sensitive to the particular material with which you work, and I would estimate it as roughly as a spontaneous strain which removes degeneracy between different domains. So for example, for nickel oxide, this could be even 10 to the minus 4 or lower if you apply in a proper direction. The other thing are the defects. So in principle, in order to move the domain wall, you need to apply infinitely small strain to remove degeneracy. Yes. But in reality, your domain wall is spin, so it's quite massive. So you need to overcome some barrier from the defects and so on. And this again is material dependent. But the strain of 10 to the minus 4 would be enough for sure. Then to simply remove one of the domain and so on.
Thank you very much.
Just like Igor Mastin suggests, you shout to your postdoc or your student, and then they will change their mind after the configuration. So Maria Azar, go ahead and ask a question, please.
Yes, thank you for the nice talk. My question is from a micromagnetic perspective. How reasonable is the assumption that in these two domains that have different strains, the anisotropy is different, but the Heisenberg antiferromagnetic exchange is still the same?
Oh, Heisenberg exchange is very strong, so it couldn't be affected by anisotropy, by so small strains. So this antiferromagnetic dynamics and all this is based on the hierarchy of the interactions. So exchange interactions are very strong. So usually typical values of the exchange fields are of the order of 1,000 of Tesla, and anisotropy fields are much smaller. And these magnetoelastic effects, they have the same order of values as the anisotropy fields. So even if you introduce some strain effects, they shouldn't change the exchange interactions in the system.
This could change if you go to artificial antiferromagnets when you can change.
Oh yeah, sure. If you
question would be relevant or would play a role. Burkhard, go ahead and unmute yourself and ask a question.
I have a question in the opposite direction. So thank you very much for the nice talk. And you excuse me. You were assuming the frozen elastic model. And that, of course, implies there is no counteraction from the magnetic system to the elastic system. But probably there is, because you should also be able to move elastic domain walls very, very easily. Is it simply outside of the model you have used, or is there anything to it? Or do you need to expand the model to take these effects into account as well?
Oh, thank you. This is a nice question. Of course, I showed only one side of the story. And of course, if you would like to consider all the effects, you need to solve the problem self-consistently, including the dynamics of the elastic system and magnetic system. But in many cases, and especially in your particular cases, in your lab, you are working with a very fast magnetic dynamics. And in this case, I can assume that the lattice is frozen, and I can apply this modeling. But of course, the magnetic system also affects on the elastic properties and so on. And we are working on this, but wait until the next talk.
Very good. Okay, I'll wait. Thank you.
Perfect. Sumit, go ahead and ask your question.
Thank you, Helen, for this talk. So my question is, when you add strain, you also make certain small changes in the electronic properties of the system. Can it play any significant role in the magnetic interaction, or it would be too small?
It's difficult to me to give the exact answer, and I think that Libor Smekal will argue that a very small variation of the properties of antiferromagnet or other system can strongly affect the electronic structure. But I think that this could be, but in a very particular material. So it's not enough only to apply strain. You should have some special topology of the Fermi surface and electronic states. The value of the strain, which is relevant to this phenomena which I discussed, is relatively small. It's 10 to the minus 5, 10 to the minus 4, could be even 10 to the minus 6. And this value of strain is usually below the accuracy of DFT calculations, or at the edge of the accuracy of DFT calculations. So I can assume that these small deformations do not change significantly the resistivity and other properties. But I cannot be sure, and maybe there are some cases where it's very important and the system is very sensitive to these strains.
So if I try to think, sorry, can I ask a question?
Yes, sure. Sorry.
If I try to think in terms of energy, how much change of energy would it cost when you use that strain? It would be a few MeV or even less?
So it should be like a micro EV something.
Okay. Thank you.
Wolfgang, go ahead and ask your question.
Yes, thank you, Elena, for the interesting and very clear talk. In principle, everything should apply also for ferromagnets. Is it just that the elastostatics is doing exactly the same thing as magnetostatics, or magnetostatics is dominating? Or in other words, can you imagine a situation where a ferromagnet is dominated by elastostatics?
So I should say that my work was inspired by the works of Kleman and Miltat, who applied this consideration, magnetoelastic consideration, to ferromagnets. So then everything which is applied to many of things which I apply to antiferromagnets also relevant to ferromagnets. And you are absolutely right that in ferromagnets we have magnetostatic effects which are usually very strong, and they can mask the other effects, the elastic effects. Mm-hmm. In antiferromagnets we usually do not have magnetostatic effects. So then this elastostatics is the only source of the long-range fields.
Yes, sure. But could there be a ferromagnet where the elastostatics is doing something else than we would expect from only magnetostatics?
So for this we need ferromagnets which have at least tetragonal symmetry. So for ferromagnets, you always have 180-degree domains, but they have the same strains. So this will not work. But if you have, for example, 90-degree easy axis or 60-degree easy axis, then of course magnetoelasticity can also play a role. And moreover, I would say that, you know, these martensites with a strong magnetostrictive effect, there are some materials in which there is this martensitic phase transition, which is associated with the electronic structure. And then you have strains of the order of 10 to the minus 2, extremely large strains. And these strains are also coupled with the magnetic structure. And so by the magnetic field, you can easily manipulate the strains and so on. And these materials are mostly ferromagnetic.
Mm-hmm. Okay, thank you.
Thank you. I think one last question is Alexander. Go ahead and unmute yourself and ask your question.
Thank you. So, Alena, thank you again for your talk. So I just would like to ask about this direction of this direct spin Hall effect in antiferromagnets and the possible tunability of this device with this trentronic, no, actually magnetoelastic coupling. So what do you think? Sorry, what do you think about this direction? So is it like can survive or something like this? So about the tunability of the for antiferromagnetic generation with antiferromagnets.
I think that it would be interesting to so there are two sides of this question. First, it's interesting to look what happens if we include strains into the dynamics, these fast magnetic dynamics, and see whether these strains are the additional degrees of freedom. So they can produce new effects which we do not have with only magnetic degrees of freedom. On the other hand, you always have this magnetoelasticity in the system, so you cannot avoid it. And we need to look at it. At least if you would like to work with an antiferromagnets, we should aware whether these strain effects are important or not. As to the spin Hall effect, I did not consider these transport properties here. So here in the yeah.
Yes. And what do you think about this magnetoelastic coupling and polycrystal antiferromagnet films? So how it can live together the polycrystalline films and magnetoelastic coupling? So how it polish, for example, each other?
So if you have a polycrystalline crystal in which the magnetic, so if you have strong exchange coupling at the grain boundaries, so then the magnetic texture is continuous through the crystallites. Then, of course, these effects would be important in polycrystalline systems, if this is what you mean. And yes, so polycrystallinity means that simply how you prepare your sample, but this magnetoelasticity is something which is peculiar to the material, so it's not related with the way how you produce your sample. Yes. Once you have effects in bulk samples, then you will have them in polycrystalline form.
Okay, thank you, Oksana, again. Thank you.
Thank you. And I think that's the last question. So I thank Helen once again for a wonderful talk, and the 200 people that showed up today to listen to you, and very nice questions that were asked. So with this, I'll stop the recording, and then I'll stop the live streaming, and okay. And